Hello, my name is Kylie Bain, and this is my Lab 2 video report. The structure of my video is as follows. To begin, the purpose of this lab was to record an object falling at a slightly slower speed than the force of gravity and to analyze the effects of drag on an object in free fall. We then plotted the position and time in Tracker and used GlowScript code to create a theoretical computer model. We'll use the momentum principle, which is also known as the Newton's second law, as well as the position update equation, and these are the equations that we will be using. Another important one is the force of drag, which is proportional to the square of the average velocity. Here you can see me drop the crumpled piece of paper. Here is the GlowScript code without the force of drag. I had to edit the ball's mass to 0.045 kilograms, as well as the initial conditions, including the ball's position and the ball's velocity. The position begins with a y component of 1.85 because that is the height it was dropped from, in meters. I also edited the delta t, which is the time step in Tracker, 0.033 seconds. The force of gravity is 9.8 on Earth, meters per second. J hat is the direction that the object is falling, which is straight down in the y direction, negative y. For this one, because there's no drag, our proportionality constant is 0. And here are the update formulas for position and velocity. When looking at the observed data versus the modeled data, we can see that the position versus time graphs are very different due to the fact that the drag force is not taken into account. This orange line is the modeled data from GlowScript, and the gray is the data from Tracker. This difference is because of the force of drag, and we will continue to look at other models with the force of drag. In order to take into account the force of drag, I had to add a few changes to the GlowScript code, including the proportionality constant, b, which I found to be 0.01 in order to make the final positions of the graph nearly the same. We'll look at that in a second. I also had to add the force of drag, which is the negative proportionality constant times the square of the velocity in the y direction, and then update the net force, which is the force of gravity plus the force of drag. Here are those results. This is the position versus time graph and model with drag, which we see a small blue arrow pointing in the upwards direction, which is slowing down the piece of paper. And the new model of this shows that it did get a lot closer, and that at the end, the final velocities of the piece of paper in the observed versus the model are very, very similar. This difference in the arch of the graph is due to the ball or the paper not speeding up fast enough, and therefore could be from a rotation in the object as it fell and a different proportionality constant of drag as time went on. Another thing we can observe from the position versus time graph here is that the object did not reach terminal velocity because this graph is still curved. If it did reach terminal velocity, which is by definition a constant and maximum velocity of a falling object, this graph would have a straight line, and it does not. So we can determine that it did not reach terminal velocity in that scenario as well as this scenario. But I did make another model with the initial velocity negative 8 meters per second, which would be if the object was thrown down. We can see that this is an almost straight line, and therefore it did at the end reach terminal velocity. To conclude, we have answered our original question asking what the effects are of drag on falling objects. We used the momentum principle and the position update formula, as well as the drag force, to create 3 different computer models for 3 scenarios. For the first 2, with and without drag, we observed that they did not reach terminal velocity because of the curve and the velocity versus time graph. However, when I edited the code to make the initial velocity 8 meters per second instead of 0, we've seen that the velocity versus time graph became much more straight and therefore did reach terminal velocity. Because we assumed the proportionality constant of drag remained constant for the object's entire fall, we had variation even when the model was with drag. Overall, we have learned that it is in fact unrealistic to ignore drag in some cases, and that it could very well affect the object reaching terminal velocity.